Hi everyone, I'm Tingting, a PhD candidate from Zhejiang University. This presentation is about mechanical property of welded hollow spherical joint with external stiffeners. It's gonna be 4 parts. First, research background. Joint is a critical part of reticulated structures. Welded hollow spherical joint has been widely used in China for decades, since it's lightweight and convenient to connect. Steel joints in service may need to be strengthened due to age-related damage, fire hazard, or unexpected overloading. Adding external stiffeners to the sphere is an effective way to strengthen it. The mechanical behaviors of welded hollow spheres and those with internal stiffener have been extensively studied, like failure mechanism, strain distribution, and load-bearing capacity, etc. Research about hollow sphere with external stiffeners first came up in 2012, but follow-up studies are inadequate. To that end, my research object is welded hollow spherical joints with external stiffeners. Experiment and numerical simulation will be used to investigate the influence of external stiffener on the yield-bearing capacity. Then all the results are summarized to propose a calculation formula for load-bearing capacity of the stiffened joint. Part 2 comes experimental research. A total of 5 specimens are manufactured and tested under axial compression. As shown in this table, specimen S1 has no external stiffener and acted as a reference group. The rest of the 4 specimens are differentiated in number, thickness, and height of external stiffeners. Instrumentation, axial deformations of the specimens are measured with 2 linear variable displacement transducers. Strain gauges and strain rosettes are attached. An electro-hydraulic servo machine with the maximum loading capacity of 10,000 kilonewtons is used to conduct these axial compressive tests. Tensile tests on 3 coupons are conducted to determine the material properties. These pictures are the failed specimens. Large pushing deformation around the circular region connecting to the steel tube are observed on specimen S1 and S2. For those used thinner stiffeners, large out-of-plane deformation occurred, and for the one used thicker stiffeners, surface flaking of the paint is observed. This is the load displacement curves of the specimens. NU is ultimate bearing capacity, and NY denotes yield bearing capacity, as shown in the picture below, which has the maximum distance to the line connecting the origin and peak point. The above graph reveals that NY and NU are effectively improved by adding external stiffeners. Then coefficient of enhancement is defined to quantify the enhancement on NY of the external stiffeners. That is, the ratio of NY of a specimen with external stiffeners to that of the one without those. It is found that the enhancement coefficient increases as number, thickness, and height of the external stiffeners increase. Part 3. Numerical research. A refined numerical model is developed using ANSYS. The overall meshed model and boundary condition is in the first picture. Constitutive relation obtained from material test is adopted. Take specimen F3 for example. Failure mode and load displacement curve obtained from numerical simulation are showing great agreement with those from experiment, and so does the load strain curves. Hence, the developed model is capable of simulating the compressive behavior of the proposed joint. The number of tests is relatively small, and the trends are not sufficiently clear to justify parametric quantification. To facilitate this effort, the calibrated model is used to carry out a parametric study of 810 cases. As shown in the table, studied parameters including the diameter and wall thickness of the hollow sphere, the diameter of the steel tube, the thickness, height, and number of the external stiffeners, which also the frequently used sizes. The enhancement coefficient ER, which was introduced before, as shown here. Following 4 pictures illustrate trends that ER linearly increases as these dimensionless parameters increase. Ignore the correlation between these parameters and multiply all these 4 variables. Envelope fitting is adopted. Calculation formula for ER is deduced. Experimental results are also plotted, which shows reasonable conservative prediction of the proposed equation. Final part, conclusion. The work presents that experimental and numerical studies are conducted on the compressive behavior of welded hollow spherical joints with external stiffeners. 5 specimens are manufactured and tested. A refined model is developed and calibrated against the experimental results. Parametric studies on a number of design variables are conducted using the calibrated model. Practical calculation formula is proposed to predict the compressive capacity. The results obtained in this study may provide guidance for the design and analysis of this type of joint. Thank you for your listening.